Welcome everyone for watching this video. In this version I'm gonna show you how to make a code in Simulink MATLAB to do something. Here in this video I'm gonna show you how to plot a projectile of a cricket ball or any kind of object in Simulink. So basically I use MATLAB. So that's MATLAB I opened already. So to start Simulink, I just click on Simulink library, and then it's gonna show after some moment. So that's that, and then you click the new model, and it's gonna come there. So what I'm gonna change is the directory. So I'm gonna change the directory here. So that's it, right? Then I'm gonna open a function because I already made it. So that's about that. I open it. So that's the function. So those who never used the Simulink have to do it. It's actually very easy to create this function block. So in untitled version I'm gonna show you. So here you can see the library browser. So you click it and you click. There are many names you can find its uses in MathWorks or in YouTube. So for example, I'm gonna show you a constant. That's actually a template which gives you a constant value, right? So you just click on it and drag it into the blank space, and that's all about that. And if you want to create the where, that's how create it. So if you want to change it, just click it inside and change the value, right? So you change the value. So I'm not gonna use that, so I'm gonna close it, right? No, right. So here I'm gonna explain you the operation of it. So we all know in Projectile, if you just integrate the acceleration, here is the acceleration function. That's the constant block, and that is, we all know the gravitational acceleration is minus 9.81 for projectile. And if you integrate it first time, then you're gonna get a value of v, right, the velocity. And if you then integrate it, then you're gonna get the position, right? So integrating it twice gives you the position. So that's the basic Simulink function. So here we use the constant block and just increase it, and then we use an integrator block. How to get it? Simple. The way I showed you before, just type integrator. Here it's already done. So just yeah, click it, and then you're gonna drag it there. How to do it in that format, I'm gonna show you. Well, you change the initial condition external so that you can get an input from the outside, and you set the external reset to rising. I'm gonna explain it later how to do it, and show the state port. So that's how you just maximize it. So that's similar to that, right? And okay, just delete it, and this is another one. Here's what you can say, the initial condition, that is internal. So if you want to change it to external, just click it there and click it there. So there's the input version of it. So what you're gonna do is just to copy it and set it there, paste it. So it's simple, and you change the value to maybe 2.44 here. That's the bowler side. Here I used it, the height of the ball where it's been released. So I just drag the cursor there to there. So that's about that. Now I'm gonna explain it to you. So if you just integrate it, the g or the gravitational acceleration one time, then you're gonna get the v, right? And then you integrate it to get the position, right? So what the function is going doing here, if you just click it here, you say the function has three input, y, v and k, and two output, v int and r. Here r is a kind of flag, so to control the integration, so I set the value -1 and v int equal k, right? So the function means something here. In projectile motion, if you just integrate it, and when the height is close to 0, here I use 0.5, it may be 0. So when it's close to 0, if you do not reset the integration, then the ball will go under the ground. So that is not expected. It's gonna have to bounce and come up. So what I'm gonna do here, I change or to reverse the value of the initial velocity, right? So -v and 0.95 here is the damping. So each time the ball bounces, it's gonna reduce the speed to 0.95 times, right? And I'm gonna change the value of r, or set the value to 1, so that it reverses or resets the flag, right? Sets the flag maybe. So that's about that. And how to write a function? Well, that's very simple. Use MATLAB, MATLAB, already there, and click it and just drag it there, right? Oh my god. Okay, man. Here, and then you can change there, right? And save it. Okay. So here's a go. So delete it. That's how you did it, right? That's very simple. So here's a word there. In this integrator, this F means the trigger, I mean, and that is connected to R, right? So that means when the height is close to 0, then the value of R gonna be changed from -1 to +1, right? And to trigger it, you just use the block or the wire to F, right? That's that. And the v int value gonna be initialized again, so it's gonna be equal k, right? That's how you just initialize the function again, or to start the integration again. So what does the k means? So it's very simple. It's the k. So to zoom it, well, that is the velocity, initial velocity, and that is the angle, the vertical angle, right? The angle with the height. So that is 145 km/h, and if you want to change it to meter per second, then you just have to multiply with 5 divided by 18, right, to get the meter per second, right? So then you're gonna have to multiply with an angle. So that's basically that, and that is the angle with radian. So input is equal to a into pi divided by 180. That gives you a radian angle, and if you sine it, if you use the sine function, then you get the output. So this is basically sine theta, right? Okay, and then if you multiply it, these two outputs, then you can get v sine theta, right? So the initial condition is actually k equal v int equal v sine theta. So that's the initial equation we all know. To integrate, v sine theta is the initial equation of the integration, and each time the ball bounces, this function initializes with it, and the flag sets from -1 to 1. So that's how we did it. And then the second time, this external, and that's how the height is defined. So 2.44 is the initial condition of the integration. So from 2.44 it's gonna be integrated. So actually the ball ain't been delivered from the ground. It will be delivered from the hand of the bowler, and the height of the hand of bowler is 2.44 meter, right? So that's why I said 2.44. So that basically gives you the y direction. And for x direction is actually very simple. So this function I've shown you before, this is meter per second for velocity, and you're gonna multiply with another function which is cos theta. Before I show you the sin theta, this basically just varies with cos instead of sin. So this is v in meter per second, and this is cos theta. And sorry, this is cos theta. So this is v in meter per second, and this is cos theta. So multiplying those gives you v cos theta, and if you integrate it you get the value of x direction, right, or x vector, whatever you might say it. And that is x and that is y. To get the z, we're gonna use another constant here, which is the horizontal angle, right? The angle with x-axis, right? And then we're gonna use tan instead of sin or cos to get tan theta, right? And to multiply with, we all know that was x, right? So multiply with tan theta gives you x tan theta, right? And we're gonna use a constant 0.6 to reduce the effect, so it gives us 0.6 x tan theta, right? And then we're gonna add it to the constant minus 1.5, which is basically the release position in the pitch, from where the ball is being released in the pitch, right? The over the wicket or around the wicket, we're gonna save the middle of the pitch is 0, so the left is minus and the right is plus. So the ball is being positioned in this case from the left, so over the wicket, right? So it's over the wicket delivery, and that's the output, and that goes to Z, right? Now I'm gonna change something. I do not need to use this one, so I'm gonna delete it. Right, that's all, finished it. And then so x, y and z, 3 input goes in a mux. And how to use mux is simple. Use mux, mux, then you're gonna get max. So this is max. You have to get 3, so just click it inside and you change the input position to 3. So 3 input. Okay, so that's how you get 3 input, right? Just elaborate this thing. Okay, so that is 3 input, right? So backspace because we don't want it. And this is the scope. Scope actually used for simulation. The x-axis of the scope is the time, and y is either x, y or z. So that is t versus another parameter, suppose x, y, z graph, right? So we're not gonna show details of that scope. We're gonna show you some another time maybe. So, and this is VR expander. Now this thing, well, we're gonna show you the value. This is actually VR realm, right? I used a design in VR realm. We're not gonna show the details of it, just we're gonna show you what to do here. Well, now we're gonna apply it. Okay, so that's about that. This is actually a VR realm form. It's based in MATLAB, so how to find it? Well, what you're gonna do here is type VRSync, right, and enter it. So it's gonna give you there. So if you just right click it and browse, then I've actually built a few models. So I use design 6, open, So that's show me that. So that's about that. And then as I use the ball position, so there are actually various routes. I just use the ball to show this function here, and that we use only translation, because to show the projectile motion we just need the translation. So we click OK. So here is that actually the similar version of that, so we don't need it, so we delete it, right? So here actually the VRSync doesn't understand from the marks actually, so we use another signal which is VR signal expander. To find it here we use this, so type VR signal and then click. So that's how we find it. To change the value in it, I just show you why we do this. To understand the VRSync, here the input is 3, right? There are 3 inputs, X, Y, and Z. So the output width will be 3, and the output signal indices will be 1, 2, 3, right? In the matrix. So that's how we're gonna do it. I'm gonna show the variables here, and we just connect it with VRSync, right? So that's about that, and we just run the simulation right here. So hope that you're gonna do it correctly. So here what I'm gonna change is I change it to infinity, right? And then run this model again. Okay, so I'm gonna click it here, and well, stop the simulation and run it again, right? So you can see the ball is coming. Balls come very slowly here actually, right? So it's a kind of disgusting thing. So if you want to fasten the pace, so just increase the speed, right? So that is actually the rate, the simulation rate. So sample time gonna be decreased. So click it and then run. So now we have first simulation, right? So that's how. Now we're gonna use a viewpoint which is better than this to me, not to any other else but to me. So I choose this simulation view, which is going to show you clearly here. It's a good view, right? Yeah. Now I'm going to change various parameters here. First, this is actually over the wicket delivery. So now I'm going to show you something. First, this is the x-axis, the length of the pitch, and the width of the pitch is the z-axis. Sorry. So length of the pitch is the x-axis, and the width of the pitch is y-axis, and the height is z-axis. So the parameters we used here, or the inputs, initial velocity, we all know that, so we don't have to explain that, and the initial release angle, or the vertical angle. The vertical angle is the angle with the height, that angle, and the horizontal angle that controls the swing, in swing or out swing, which is with x-axis, right? This axis. So if we draw a line like this, so it will be maybe 5 or 10 degree. Similar here, from the around the wicket, it's gonna be minus 5 or 10 degree, right? And the bowler's position gonna be bowler's height gonna be that high or that high, right? Any kind of height you see. So that is the value of C, and the bounce gonna be selected with the vertical angle. So if you just increase the angle, that there are gonna be more bounce, or decrease the angle, that's gonna be close to resistance, so it's gonna be a York or something. So, and you can also vary the speed to get different results. So we're gonna show you the results here. So first we're gonna give you around the wicket delivery. So to get around the wicket delivery, we're gonna use 1.5, right? 1.5. So okay, and the angle gonna be minus 8, and this thing actually same. it gets same, and now we're gonna show it. So stop the simulation and run it again. Yeah, so that's a random wicket delivery. That's a very good delivery actually. So I just say this is 0 for z-axis, this is 0, and this is plus 1.5 and this is minus 1.5, right? So I used minus 1.5. So basically it's around the wicket delivery, and the angle was minus cause this angle I do not change the vertical angle, I kept same, but the line for outswing I use this angle minus 8, so it creates minus 8 degree angle with x-axis, right? This x. Okay, so that is a random wicket delivery. To make the bounce variable, what I'm going to do is to increase the vertical angle, right? So I increase the vertical angle and simulate it again. So now we're gonna change, we're gonna see the change of bounce. So basically this is more of a bounce delivery, right? Well, and then it is a very slow process, so to fasten the process I gonna fasten sample rate. So now we're gonna show how fast it is. Yeah, that is how fast a batsman faces the delivery from a fast bowler, right? Yeah, that fast. See that? That is actually very dangerous, right? And if we want to change the height of the delivery, just click it there and change it to maybe 3 meter height. Is that good? I think it is. So do it and run the simulation, right? So here it is. Stop it and run it. Yeah, it's basically the height has been changed. It's more of a high ball, so taller fast bowler. So yeah, that's how fast it is. So thank you everyone for watching. Hope this video will be helpful for you to build your own simulation model in Simulink, and yeah, thank you for seeing this. Goodbye.